At is this idea of an exponential growth or decay function. An exponential growth or decay function grows or shrinks at a constant percent rate. And so what are the key points that we're looking at with here? Your equations are going to look like f of x equals a 1 plus r to the x, or they're going to look like f of x equals a b to the x. And what the key difference is here is you can see that this 1 plus r is being replaced with b, and that's because they're letting b equal that. And we'll be able to figure out which one we need to use. Key takeaways with this and what we want to make sure we understand. A is always going to be your initial or starting value. R is going to be your percent growth or decay rate. Make sure you write it as a decimal. Don't use that percent number. And then B is known as your growth factor or growth multiplier. And so that's where the difference of when do I use the B, when do I use the R. So let's just jump right into some problems and see what we're looking at here. India's population of 1.14 billion in the year 2008 had a percent growth rate of 1.34%. Write an exponential function for India's population and use it to predict the population in 2020. So a couple of key takeaways that we want to look at this one. It says India's population of 1.14 billion was in the year 2008. It had a percent growth rate of 1.34%. And what we want to do is we want to write an exponential, and then we want to predict the population in 2020. So first, let's start with our formula. F of t is equal to a 1 plus r to the t. And so that was our formula we first wrote down. Now, things that we know about this. We know a is our initial or starting value. And so in a lot of times when you're looking at years, so this one's looking at 2008 and then 2020, we don't use the 4-digit year. We start with 2008 and we call that our 0 year. So if 2008 is our 0 year, that means that amount of 1.14 billion is our initial or starting value. So I can say f of t is equal to 1.14. And again, you'll notice we're using 1.14 to represent how much is the population in billions. And we're not using a whole bunch of zeros with that. The next part said that it had a percent growth rate of 1.34%. So since that growth rate was 1.34%, don't forget we got to change those percents to a decimal. And so that means for your R, I'm going to use 0.0134. And so I'll come over here and this will be 1 plus 0.0134 raised to the t. So if I clean up this formula here, I have f of t equal to 1.14, 1.0134, I just added those two together, t, and I now have that first part where it says write an exponential function. The next part says use it to predict the population in 2020. So again, when we're working with this year of 2020, we're not going to use a 4-digit year. We're going to adjust that, and since the year 2008, that's 12 years away from our starting year, so we're going to use a t value of 12. So for that next part, we're going to say what is f of 12? Well, that's 1.14, 1.134 raised to the 12th power. So let me show you how we can plug that into the calculator and get our result. And so we're just going to plug in what we just got. So I'm going to say 1.14, open parentheses. I want 1.014134, close parentheses. I'm going to use that A to the B button and raise it to the 12th power. So you want to make sure that 12 is up in the exponent. Now this says 1.3374. And so what we'll do is we'll round that and we'll just kind of auto go to 3 decimal places. And so we're looking at 1.3374 to round. So we would say this is equal to 1.3374. I'm going to round to 3 decimal places. So I'm going to look at that 4. It's not 5 or greater, so that gives me 1.337. And just follow the rules of whatever that problem states. In rounding, I always kind of default to 3 decimal places. That's kind of my go-to. Let's look at the next one. This is a decay problem. So that first one dealt with growth. This next one's going to deal with decay. And so it says, bismuth-210 is an isotope that radioactively decays by about 13% each day, meaning 13% of the remaining bismuth-210 transforms into another atom, polonium-210 in this case, each day. If you begin with 100 milligrams of bismuth-210, how much remains after 1 week? Hope I didn't just lose you reading out that problem. Let's look at that paragraph again and look at our takeaway here. This one says that it decays. That's important because what we're going to be looking at is subtraction with this problem. Then it says by about 13% each day. So that is our decaying rate. So when I'm looking at what is my rate in this problem, it's going to be negative 13%. Change it to a decimal, so negative 0.13. Now down here it said that if you begin with 100 milligrams, so that means my initial or starting value is going to be that 100 milligrams. So when I go to set this up, this would be f of d, d is in days. So my initial value would be 100. And then because it's decaying, it's going to be 1 minus 0.13 raised to that. And we're using d just to represent our time in days. I could clean this up. This gives me f of d equal to 100. Now 1 minus 0.13 is 0.87 to the d. So this will represent any amount of days that I want to look at and see how much bismuth is going to remain. Don't get distracted in this problem that it does say 210, 210. We're never going to use the 210. That is just a part of the name of it. Now this said, what is it after 1 week? Well, I'm not going to use 1, and I was being very detailed with using D for day because after 1 week doesn't mean plug in 1. That means plug in 7. So we need to be careful with that. And the reason we know that we're going to be plugging in 7 is because our rate is based off each day. So I would say then f of 7 would be equal to 100 to the 0.7 raised to the 7. Again, just like you've seen our other calculations, I think you can trust how I've gotten that number. That gives me 37.725 milligrams and just rounding to 3 decimal places. And so I just really want to point out that part there too. This is after 7 days. So I'm not plugging in 1 because my growth rate, or that 0.13, was in terms of days. And then we've gotten our final answer. So with these, you can see when we're looking at these different formulas, some of them they're just plugging into there. What we have not used is that f of x equals ab to the x. So let's look at that. This is finding equations of exponential functions without knowing the rate of growth or decay. So that's when you know you want to go into this formula. This problem says, in 2009, 80 deer were reintroduced into a wildlife refuge area from which the population had previously been hunted to elimination. By 2015, the population had grown to 180 deer. If this population grows exponentially, find a formula for the function. So the fact that this was growing exponentially is going to cue me on to use one of those formulas. It doesn't tell me a growth rate or anything. So here are the steps that I'm going to have to follow. I first want to make 2 points. So I want to kind of pull our data from this paragraph. So I can see that in 2009, there was 80 deer. So that means in 2009, that's going to be our starting year. And so I'm going to say at year 0, I have 80 deer. And then I can see that it says in 2015, it has grown to 180 deer. So in 2015, so let's see, how many years has passed from 9 to 15? That's 6 years. And so we now have 180 deer. And so what I'm going to do is I'm going to take those 2 points and I'm going to use that information to help me to figure out the rest of the pieces to this puzzle. Now we are using the formula just so we have it right here in front of us. F of t equal to AB to the t. And remember, this A right here is our initial or starting value. It says 80 deer were reintroduced. So this is our start right here. So when I go down here to create this is F of t is equal to A, which is 80, my starting value, B to the t. And so what I want to do is, this one helped me to see that initial value. So I'm going to use this second piece here. I'm going to use to find my B value. So I'll say, okay, well then that means 80 we got from that initial value. B, after 6 years have passed, I have 180 deer. And so I'm going to take that piece right there and I'm going to solve that for this B value. So let's kind of jot that down. So I want to solve for B. So I'm going to use what I have, 180 equal to 80 B to the 6. I'm going to get that B by itself. So I'll divide both sides by 80. That gives me B to the 6 equal to 18 over 8. Again, just using your on-screen calculator. In order to get rid of the 6th power, I would have to 6th root. And that gives me B equal to the 6th root of 18 over 8. Would just reduce down to 1.1447. And I would just use my on-screen calculator to do that 6th root. So my final answer, because it said to find a formula for the function, that's our goal. So we started with 80. We figured out that B value to be 1.1447 raised to the t power. So with this one, it was different because I didn't have a growth rate. So I wanted to use the AB raised to the variable. And then I wanted to use my other value in order to solve for B. Now this is not all we can do with this. We can do some other exponentials with it as well.